So welcome to Physics 1220. Some thoughts on light. Newton said light, because it travels in a straight line, has to be a particle. Several centuries later, Young did his double slit experiment, and light diffracted and interfered in that experiment, and consequently it had to be a wave, because that's what waves do. More on that in a few classes. So light is a wave, according to Young. Further evidence for the wave theory came when Maxwell developed the theory of electromagnetic waves, and then Hertz found them. So light, being on the electromagnetic spectrum, had to be a wave like all other electromagnetic phenomena. But this century, in order to explain the photoelectric effect, Einstein realized that light actually was made up of little bits of energy, which he called photons. And if it's been a little bit, then it's got to be a particle. So what we've got then is a duality. Light displays both particle and wave-like properties. Really, it isn't either. It's not a particle because it bends when it goes through a slit instead of going straight through. And it's not a wave, well, because it's got a granularity, and also because it travels through space through a vacuum where there's no medium, and waves need a medium to travel through. So what is it really? Well, fundamentally, the quantum mechanical theory of light is that it's made up of photons. Light is photons. It's little bits of electromagnetic energy. What produces these photons? Well, vibrations of charged particles in the atom, the electron bouncing back and forth. What are the properties of light? Well, light has a bunch of wave properties. The first one is the wave equation. The product of the wavelength and frequency equals the speed of the wave. And for light, that's 3 times 10 to the 8 meters per second. Light will also reflect, refract, diffract, interfere, and so on. Light also has quantum mechanical properties that we'll get to in a few classes. So let's start with the first of these wave properties. I guess the second, reflection. Now, when a wave encounters a boundary, some wave energy bounces back. That's what reflection means. And if we consider the light ray striking a surface, this could be a piece of glass, it could be a piece of polished metal. When the light strikes that surface, so here's the incoming light ray here, then it's going to bounce back. And how it bounces back, bounces off the surface, reflects in a very particular way. If we consider this imaginary normal line, which is perpendicular to the surface, then this angle here, which we're going to call the angle of incidence I, is always going to equal the angle of reflection, which we'll call R. This is the law of reflection. Angle of incidence equals angle of reflection. Now, of course, not all of the wave energy, not all of it bounces back. Some of it actually goes through the material. It doesn't necessarily follow the same trajectory that it was going earlier. In fact, it tends to bend a little bit. More on that later. Now, the law of reflection also applies to rough and curved surfaces. So if you have a rough surface here, and you've got an incoming ray of light, then you would first draw a tangent to the surface, and then perpendicular to that, you would draw a normal line. This will tell you the angle of incidence, and then the reflected angle will just equal. So you have to do that construction, tangent, normal, in order to draw the reflected ray. Now, for a curved surface, something really interesting happens. So incoming light ray, tangent, and then perpendicular, normal. Then just make the angle of incidence equal to the angle of reflection. And what we find if we draw another ray over here and repeat that process is that parallel rays, a whole bunch of parallel rays, will all get bent and focused at a focal point. And that's characteristic of curved reflectors. And that just comes from the reflection law. All right, here's some very simple reflection problems that really just boil down to grade 8 geometry. You can give those a try. In terms of, we'll start with, whoops, let's undo that. We'll start with reflection in a plane mirror. This is really just a review of Physics 11. What we should realize is that an object, all points on the object are emitting light in all directions. Some of that light will enter your eye. So this is a physics eye. And the light that actually enters your eye, there's a cone of light coming off this object that will actually make it into your eye through the pupil opening. Most of the light coming off the object doesn't, but there's a cone that does. Now, when you're viewing an object by reflection, and if you're wondering why I have to do this, it's just because I can't write on the Word document, unfortunately. So what will happen is some of the light coming off this object is going to bounce off and go like that. And so the cone of light that makes its way into your eye obeys the reflection law at this surface. But of course what your eye does is it focuses this, and these lines are already nicely drawn for you over here. You just need to add in those two. Your eye will focus this back to an image over here in behind the plane of the flat mirror. Now, of course, there isn't really anything there, so we say that this is a virtual image. The light appears to come from here, but of course there isn't really anything there. The image size is the same as the size of the object. The distance is the same from the mirror, object to mirror and mirror to image. Those two distances are the same. It's upright, so there's been no change in our vertical orientation. Horizontally, it's left and right inverted. So if you reach out your right hand to the mirror, it appears to be reaching out its left to you. Okay. Now, you can, if you get two flat mirrors and vary the angle between them, get a larger number of images. These arise from multiple reflections. So for the case of 90 degrees, if we put an object here, there's the object, we expect, one image here from this mirror, another image, let's see, about down here. And this is how you draw a physics eye, by the way. Draw a wedge, draw an arc, draw a pupil. There you go. Okay, so some light is going to go like that and get into your eye. Some light is going to come this way and bounce into your eye. And then way over about here, some light is actually going to bounce off both mirrors like that. And so that's how you get the third image. Okay? So 1, 2, 3 images when it's 90 degrees. And you could try the experiment to see how many images you get when it's a different angle, say 120 or 60. Okay, here are some very simple image questions. And now we get to some core content, which is images in curved reflectors, not in flat mirrors anymore, but in curved mirrors. We are going to focus then on, no pun intended, on 3 locator rays, which are going to help us identify the location and nature of the image. Now, it would be wonderful to be able to draw on this document, but I can't really. It won't even let me pick the drawing tool anymore. So I'll have to get by with drawings over here on my tablet. So, if I do it slowly, it may work here. Already not off to a good start. Okay, so there's our curved reflector. Now, you'll notice there's 2 points here. F is the focal point. C is the optical center. The 3 locator rays are as follows. Let's say we have an object out here. Okay, this might be a candle flame or a person or something like that. So the first locator ray is parallel to the principal axis, will bend through the focal point. Okay, that's we mentioned earlier. So you could just draw that on here. Draw an object, draw a ray parallel to the principal axis going through the focus. I should say over here that this line is called the principal axis. Okay, it's just a line of symmetry. Next locator ray any ray that passes through the focal point will reflect parallel to the principal axis. That's our second locator ray. And then our third one here's the focal point, is the optical center. Any ray passing through the optical center will reflect back on itself. So these two lines should be straight, but it won't let me use a ruler on my tablet. So you can, though. So any ray passing through the optical center reflects right back on itself. Those are our three locator rays. And we can use those to identify the location and nature of the image. Now, we're going to use an approximation here, which is known as the thin mirror approximation. And that means that instead of drawing those reflections at the mirror's surface, okay, we're going to assume that the curvature is really small, and therefore that the reflection happens essentially on a vertical line. So if we consider our three locator rays, the first one is parallel to the principal axis, reflects through the focus. So notice that I drew it all the way to this vertical axis and not the surface of the mirror. The second one, through the focal point, reflects parallel to the principal axis. And then the third and final locator ray, anything through the optical center, reflects right back on itself. Now, what we see here, though, then, is that those three locator rays should all meet at a point, okay? And that point where they meet, that is the image point. So you can just draw the same diagram here on the next page, and then you can identify this as the image point. Now, any rays traveling from this object are going to hit the mirror and reflect through that image point. We just use the locator rays to find out where that image point is. So, although we just have these three locator rays, the actual geometry of varies a bit depending on where the object is. So there's really four different cases that are going to emerge. Let's go through those four now. So first of all, we're going to have a concave / converging mirror, like I've been drawing so far, and a distant object. So an object way out here beyond the optical center. So let's see what happens when we do that. All right, so here's the focal point, here's the optical center. And so let's put an object way out here, and let's just draw a locator ray. So parallel to the principal axis. Oh, I forgot. I've got to draw this vertical axis because we're going to use the thin mirror approximation, which means that my ray parallel to the principal axis goes all the way back to this vertical axis and then reflects through the focal point. So there's my first locator ray. My second one is going to go through the focal point, and then it's going to reflect parallel to the principal axis. Now, those two locator rays met right here. The third one will also go meet there, but I don't need to draw it because I can see that that ray right there is going to line up with those points in the mirror. So the two locator rays, once they meet, it's sufficient to identify the location of the image. So what this would look like if you were looking at it is a tiny upside down version of the object. So we can say that our image, we can write some characteristics of it. Our image is going to be, first of all, a real image because the light actually meets at that point. Okay, there's no focusing action of the eye that's required. This is a real image that you can project on a screen. So it's real. We can see that it's inverted because it's upside down. And for a really, really distant object, it will also be a small image. Okay, so that is the first ray drawing to master. Now, something will change if the object gets close, okay? So if the object comes in here and let's say is inside the focal point, we're still going to draw those three locator rays, but we're going to see they're going to meet at a different spot. So how does it look then if we put the object inside the focal length? So here's the vertical axis, here's the curved reflector, Here's our focal point right here, our optical center, and now we're going to have a close object here. Well, we still draw the three located rays. Parallel to the principal axis, reflects through the focal point, just like that. Now, for the second located ray, you can't go from the object through the focus and hit the mirror. So we're actually going to line up the focal point and the object, and that ray, which is aligned with the focal point, is now going to reflect and go parallel to the principal axis, just like that. Okay? So ray 2 is aligned with the focal point and reflects parallel to the principal axis. So now, clearly, these two rays don't meet. They're diverging. But if you looked here with your physics eye, your eye would see an image at the common point of origin, which is back here. So this image, first of all, it's virtual, because these light rays don't actually meet. You can't project an image on a screen. You have to look through your eye and see it back in here behind the plane of the mirror. There's clearly no light back here. That's another characteristic of virtual images. So it's virtual. It's upright. And it's large. So the same two located rays give us quite different behavior when the object is inside the focal length. And you'll have to keep that straight. Okay, that's the second diagram. As we see here, that second ray, oh, I've written it out, how nice. This second ray is aligned with the focal point, comes past the tip of the object, and then reflects parallel to the principal axis. Okay, two more drawings. Okay, what happens if the object is actually at the focal point? So let's again draw principal axis. In the thin mirror approximation, the reflection will happen right there. Okay, so here's the focal point. Here's the optical center. So now we're actually going to put the object right here. Okay, so parallel to the principal axis, reflects through the focal point. And then clearly we can't draw the second ray because we can't go from the tip of the object through the focal point and hit the mirror. So we're going to have to draw the third ray, remember, which is through the optical center and reflects back on itself. So here we are through the optical center. I was supposed to hit the tip of the object there, but I missed. And then it reflects back on itself like that. Now we have a problem. These two rays don't meet. Because they're parallel. So in fact, there's no image here. Or another way to put it, as we'll see in a day or two, is that the image is at infinity. Okay, so when the object is at the focal point, there's no image. If it's out here, then there's a real inverted and small image. If it's in here, then there's a virtual upright and large image. If it's at the focal point, there's no image at all. So that's 1, 2, 3. Those are the 3 of the 4 ray drawings that we need. One more. Now, a convex reflector. Okay, so if you look at, say, a soup spoon, you've got one concave side and you've got one convex side. The convex side is the concave side is focusing. Okay, so what we've been saying here, concave or converging or focusing mirror. Those are all 3 equivalent descriptions. The concave mirror is a diverging mirror. Let's see what its ray drawing looks like. So now here's the mirrored surface right here. So this is like, say, the rear view mirror in your car or a store security mirror. Here's the vertical axis, and then the focal point and the optical center are over here on this side. All right, so an object over here, parallel to the principal axis, is going to reflect through the focal point. Well, clearly no light goes through the mirror, so what's going to happen is it's going to reflect as if it came from the focal point. Okay, so ray 1 reflects as if it came from the focal point F. Ray 2 is going to be heading for the focal point. So let's try drawing that. I think I got it. So it was headed for the focal point. It's obviously not going to reach it. At that point, it's going to reflect parallel to the principal axis. Okay, and then the third one, we won't even draw it but the ray heading for the optical center will just reflect back on itself. So these two rays are diverging, there's no image. But once again, if you look through with your physics eye, your eye will focus those rays back to where they seem to originate from. You'll get a tiny image back here, just like that. So that image is, once again, virtual because it's behind the mirror. There's no light here. It's a creation of your eye. It's upright, and it is small. So it's small, upright, and virtual, SUV if you like. And that, of course, is characteristic of what you see in your rearview mirror. And this is, of course, why they print that warning that objects are smaller than they appear, because it may be that the mirror is making the image small and thinking the dude is far away, but it really isn't. All right, so some notes here. As we said, if the reflected rays actually meet, we get a real image. If they don't meet, then we focus backwards to find the virtual image. So these are some notes then on the ray drawings and those 4 diagrams you need to remember. When we meet in class on Monday, we're going to start by doing an example together, and then you can hopefully be up to speed then on how we're going to draw these drawings. We're going to do this again next